data, which is reported incidents of flooding which cause significant damage. So it's the intersection of the human side with the intensity of the flood, and this is the location of 3,700 plus events that these people have recorded between 1985 and 2010. So that gives you a sense of places which are sort of floody more than others in terms of, again, intersection with the human side of the story. So the sample size is fairly large covering that time period. Now, there are reporting issues with all these things. So primarily what I'll do is to avoid getting into the details of that. I'm going to look at data between primarily 2001 and 2010, where probably reporting issues are not that different from other periods. So if we look at it that way, the number of floods that are being reported here globally increases and decreases over time. 2010, which the media was jumping on as one of the major flood years, actually is not particularly prominent. The lower figure shows you the climatology of all these floods. So we see that June, July, August, September are perhaps the floodiest period globally. Northern hemisphere, because that's where much of the population is, and the intersection comes with some activity also in other seasons. Those are flood counts all the way through. This is a combination of how these floods are distributed over the year and across these years. And what you see is that there are active and inactive June, July, August periods, and then periodically you get bursts of floods in other seasons as well. The floodiness varies across these time periods. So the reason I motivate this particular picture is that at least in terms of damage reduction and mapping, it gives us some sense of which seasons we should focus efforts on, and whether the prediction can be binary in the sense of, is this going to be a very active season or not? Similar to what people do with the hurricane sort of story. So what I'm going to do starting out is to look at January, February, March, which is not the floodiest season, but to motivate a particular thing. And here are probability distributions of the latitude at which the flood occurs in this particular season across a selected 5-year period. And this is taking all the locations where there's a flood, doing a probability distribution versus latitude using a kernel density, and separately for each year. So there are some differences here. Primarily, you're getting floods in the southern hemisphere, but periodically, the northern hemisphere also starts seeing some floods in this period. The motivation here is right here. My hypothesis is that meridional water transport from the equator plays a big role in determining the latitudes at which the floods happen. And so if I'm looking at it globally, I would like to start out looking at it that way. So the red dots are where the floods occurred in this particular year. If it is blue, going to the southern hemisphere, that is positive motion in that direction. If it is red in the northern hemisphere, that is positive motion of water vapor. So you can see that in this particular year, we have 55 floods occurring in that season, and the dots match up generally well with where the moisture transport is taking place. We go to the next year, the floods switch to the south in the northern hemisphere and are more intense in the southern hemisphere and line up nicely with the tracks. Similarly, as we go through this animation, you'll see each year works out the same way. So this is something I've shown at AGU a few times now, and I'll show it here again. And the motivation here is that we've looked at floods along the west coast of the United States, and we've found that there is significant predictability season ahead for these in a cross-validated sense. And it's motivated first of all by this figure. We look up and down the coast, and for each one of these states, we have looked at the 10 largest flood seasons and the 10 smallest flood seasons for that particular location. And we've looked at the associated sea surface temperatures, and what you see is that this picture here, where you get the 10 smallest floods in the northwest, corresponds to the 10 largest floods in the southwest, and vice versa. So this demonstrates the kind of structure that you end up with by latitude, and to a certain extent in the sea surface temperature picture by longitude in terms of what drives flood in this place. Here's an example of 4 randomly chosen sites in 4 areas in the western United States out of 124 sites. And these are cross-validated probabilistic forecasts using only 4 predictors: the ENSO index, the trend in the ENSO index, the Pacific Decadal Oscillation, and the trend in the Pacific Decadal Oscillation. The numbers in each box represent the variance in the annual maximum flood at each of these sites that was not explained by the model, and the bars show the confidence limits associated with it. So the second thing I want to show you here is what happens in June, July, August, the floodiest season. So here I'm trying to show you at the bottom the counts of floods in each of these years. So there's quite a bit of variation there. And then the spatial distribution or the spatial probability distribution of floods. This is longitude, this is latitude. And you see that there's a bullseye here in terms of the highest area of floodiness, and there's some other things. As I go through, you will see the probability distribution move latitudinally and longitudinally. So 2002 is interesting, keep this in mind. We had an extension to the north. 2003 we come back. 2004 we go right back to the same sort of situation. 2005 is like 2003. Shrinkage again, and so on. So each one of these seems to have a distinct sort of character, and the argument I'm trying to advance here, no floods at all in the southern hemisphere 2010 incidentally. It's all concentrated in that zone, even though this is not one of the very flooding years. So the idea is that these are canonical signatures of global floods. That's what you're seeing here. And if we can actually identify these signatures and then the moisture transport signatures that correspond to these, and sea surface temperatures and moisture source signatures associated with this, we may have an ability to do something about predicting these things with or without climate models. So the same set of stuff, but looking latitudinally only. If you look at the probability distributions associated with these individual years, these are some rough groupings of very similar probability distributions, basically where the floods are occurring by latitude across these years. And what I do here is I grab 2002 and 2004, which are sort of similar, and these are eastward moisture fluxes by latitude, and these are northward moisture fluxes by latitude and longitude. And you see that they are quite similar across these years. And when I switch to the next pair, which is 2006 and 2010, which have a similar to each other but different from the other probability distribution in terms of the spatial expression of floods, they again now have a common structure across themselves but different from the previous one in terms of both the strength and the sources of moisture transport. So the idea is that if we can harness these, and we have done some work in this direction which shows that there is a possibility of doing this, then we can put together a strategy for what I'm calling dynamic risk management in terms of a global sort of structure, where we recognize that there are multiple means by which climate change is going to propagate through the system, and it's in any case going to be risk which is changing by time, year by year, through clusters of years, and across the century. Some of this may be predictable by various means, the rest will not be. And if the part that is predictable can be parsed into two things: near-term evolution, or prediction a season ahead perhaps, or long-term statistics, which is what is the nature of clustering in these things. And that's important if you're going to write insurance policies. You want to know whether or not your payouts are clustered or not, and then how to structure the risk product in accordance with that. These can also be used for infrastructure design and operation rules. Today we use the principle of stationarity, which assumes that the risk we face is the same every year. And so we have a lost opportunity in that sense, because we don't recognize that if we have clustering of these events, or we can predict them, we can adjust both the operation of existing infrastructure as well as maintenance schedules, as well as the layering of financial instruments that can help you balance these risks. So that's basically the idea that I'm promoting. And to summarize, what we have started at Columbia, and I would invite others to join, is a global flood project that is aimed at understanding and predicting the global distribution and occurrence of floods consequent to identifiable ocean atmosphere conditions. And we can use models for this, reanalysis or prediction models. There's no choice without using some models that interpolate the ocean and atmosphere data. And clearly, this will help us do flood risk management and climate change adaptation, but I think most importantly, this is going to help the fundamental science, because when we have examined in our group how the climate models, GCMs or RCMs perform as to the details of circulation that is important for hydrological transport, whether it's for extreme events or for normal events, they are significantly biased. If they are significantly biased, then it's very difficult to know what to do with them in terms of future predictions. So if we can work on identifying empirically what the structures are that those models need to reproduce, particularly for extremes where the signal to noise ratio is presumably higher, then those improved parameterizations may help improve the overall structure of the models. And one comment I'll make here is that many times we think that it's the temperature fields that drive circulation that drive precipitation. But if you look at the synoptic structure of extreme precipitation events, their associated latent heat release has significant impacts on the circulation structure itself. And this is not really captured very well at all by the models. And that's something that we have to actually pick up on. So that's the physical science side, and I'm arguing that a parallel initiative is needed which thinks about how risk management applications, particularly in the financial markets, can be structured to take advantage of knowledge that is emerging in terms of global flood risk. If you have spatial structure, if you have space and time correlated structure, the opportunity to average across this provides an opportunity to dramatically reduce the cost of such coverage and to adapt these things to something. This, I think, is the major opportunity in all this. Knowing that I have 15 minutes and I wanted to just get a few ideas across, I focused on those, and I'm going to highlight a few talks by or presentations by our group at this meeting where you might be able to learn some more, particularly the first one, which is tomorrow, where we will show that over Brazil, it's possible to predict at ungauged and gauged locations using a Bayesian model the flood risk for the upcoming season using rather few predictors. Thank you very much.
Dry land, a bad thing, where in the past it was a neutral thing?
No, that's a good question. That's exactly what I was alluding to in the beginning. I only use the last 5 or 10 years of data because the assumption is that over that period this is not a significant issue. But in general, you're right. The other comment I would make on that is that the enhanced initiative that our leaders indicated in the beginning, that does essentially imply looking at the intersection across the two. So you would have, if you were doing predictions, you would have to integrate both factors.